Hi, our group's topic is about autonomous delivery with obstacle avoidance. So we seek to design a time-optimal controller for autonomous delivery. Currently, there are robots that implemented in hotels and restaurants to deliver food and drinks, but they cannot address time-optimal purposes, especially when they counter dynamic obstacles such as people walking in the planned path. They would wait for them to move out of the way instead of detouring for the purpose of time optimal. So the model predictive control algorithm allow us to plan for a time optimal trajectory while having a dynamic obstacle constraints. And here is the flowchart of our design obstacle avoidance method. So we generate a grid map and use A-star algorithm to generate our X and Y reference for the MPC controller. We also need an angle reference because of the way we set up our dynamic models. Then we implement OBCA, the optimization-based collision avoidance method. And within that, there's an MPC controller, which will output the time-optimized trajectory and optimum input.
In this case, we consider the dynamic of the delivery robot as a vehicle, and therefore the dynamic model is a non-linear continuity time model. The state space equation of the system are shown in the slide. X and Y are the global coordinate in the grid map. V is the velocity of the robot, and phi is the angle of current velocity with respect to global x-axis. For computational conveniences, we discretize the system using Euler discretization and set x, y, phi as the state variable, the velocity and the angular acceleration as the input variables. A-star searching algorithm is a commonly used path-finding algorithm because of its simplicity and speed. Through use alone, it does not determine a dynamic feasible trajectory. We use the A-star to provide an initial predicted trajectory for reducing the large number of repeated computation caused by complex maps. We first grade the map according to the true size and create nodes. The A-star algorithm will calculate the cost of each enabling node from the start point, and the final cost is the sum of the cost of each step.
Our control problem is to go to the target position with collision avoidance, and the method for use is optimization-based collision avoidance, the OBC-MPC. In the model, the obstacles and the four-dimension car model are represented as hyperplane. And because we hope to have a fast response on the obstacle avoidance, but still want to satisfy the terminal constraint, so we add a decision variable t to tune the sampling time, and then the problem can be feasible even with a short horizon n. The OBC-MPC may spend a lot of time to find the optimal solution when the map is large and complex. So we first generate the reference trajectory with A-star, and then use a short horizon OBC-MPC to do the reference checking. Inside the MPC, there is one based on the constant sampling time, and another one has the decision variable t. When the sensor detects the dynamic obstacles, we will use the constant sampling time OBC-MPC. And the sampling time is given by the first type of MPC, and we will calculate all the obstacle constraints at every time step outside the MPC and give it into the second type.
We generated a closed-loop MPC simulation as shown in the GIF on the left. The span time on the top is the real time that our dining car spent to achieve corresponding positions. The blue dotted line is the reference route we generated prior to the closed-loop simulation, which is generated from the A-star. Orange dots are the past position that the dining car went through, and the purple dots are an open loop positions that our MPC generated within every closed loop. And the big green and red circle represents our simulated ladder with the radius of 8 meters. As far as there is no dynamic obstacles, the ladder circle remains green, and while a dynamic obstacle comes into the range, the circle turns to red, and we switch to the second MPC in solving both static and dynamic obstacles. In our interest of getting rid of the reference tracking, we try to use only starting positions, terminal positions, and MPC to solve only static obstacle cases, but it is interesting that the passover choice is significantly different from the one generated by A star. We inferred that the distance error comes into the cost function, pushes the NPC to choose a different one. In general, we successfully designed a closed-loop NPC for our dining car, achieving purposes of reference tracking, obstacle avoidance, including both static and dynamic ones. If we want to expand our project, we hope we can add more complexity into the map and A-star paths for more real-world cases, like irregular movement of our obstacle and etc. We did try a more complex dynamic obstacle cases and show in the next two GIFs. The first one is when our dining car is facing two dynamic obstacles in a closed loop, and it cannot see the second obstacle until it goes past the first one totally. And as you can see in the GIF, the illustration shows that the car passes to dynamic obstacles successfully. The second case is when our car is facing one static and one dynamic obstacle, and it cannot see the second one until it passes the first one. And both cases were simulated successfully, but we did not put those into our overall simulation in the closed loop because of the time limits. And that will be all for our presentation. Thank you.